Welcome back, everyone, to the Deep Dive. We spent a lot of time on this show talking about things that are, well, pretty big, like planets, stars, galaxies, that sort of thing.
It's true, we do love a good cosmic scale topic.
But today, we're shifting gears. We're going small, really small.
Microscopic even.
We're talking about the nucleus, the very heart of the atom.
Exactly, and by understanding the nucleus, we can unlock so many secrets about how the universe works at its most fundamental level.
Right. We're going to explore nuclear physics. That means the particles that make up the nucleus, the forces that hold it together, and the processes that occur within it, like radioactivity, fission, fusion.
All that good stuff. And not only that, but we'll also touch on some of the practical applications of nuclear physics, from medicine to energy production to figuring out how old things are.
It's a big topic, but we're going to do our best to make it clear, concise, and hopefully pretty fun.
No equations, I promise.
So buckle up, folks, and get ready to dive deep into the fascinating world of nuclear physics. Let's start with the basics. The nucleus. What is it and what's it made of?
Well, imagine the atom as a vast, mostly empty cathedral. At its very center sits the nucleus, a tiny, incredibly dense sphere. It's like a pearl hidden within a giant oyster shell.
And this curl, so to speak, contains almost all of the atom's mass, right?
Yes, that's right. And it also carries a positive electrical charge.
Okay, so what exactly is packed inside this tiny, positively charged pearl?
The nucleus is made up of two types of particles, protons and neutrons. We call them nucleons.
Protons and neutrons. I vaguely remember those from high school chemistry. Remind me what they are again?
Sure. Protons have a positive electrical charge, while neutrons, as their name suggests, are neutral. They have no charge.
And it's the number of protons that determines what element an atom is, right?
Exactly. That's the atomic number, which is often represented by the letter Z. So, for example, hydrogen has an atomic number of 1 because it has 1 proton in its nucleus, while carbon has an atomic number of 6 because it has 6 protons.
So the periodic table is basically arranged by the number of protons in each element's nucleus.
Precisely. And then we have the neutrons, which, along with the protons, contribute to the atom's mass. The total number of protons and neutrons in a nucleus is called the mass number, denoted by the letter A.
So A equals Z plus N, like a little equation.
Exactly. Simple as that.
Now, we often hear about isotopes. How do they fit into all of this?
Well, isotopes are atoms of the same element that have the same number of protons but a different number of neutrons. So they have the same atomic number, Z, but different mass numbers, A.
So they're like variations of the same element, but with slightly different weights.
Precisely. A good example is carbon. The most common isotope of carbon is carbon-12, which has 6 protons and 6 neutrons. But there's also carbon-14, which has 6 protons but 8 neutrons.
And both are still carbon, just with different numbers of those neutral neutrons. Okay, so we've got these protons and neutrons packed together in this tiny nucleus. How small are we talking exactly?
The nucleus is incredibly small, even compared to the already tiny atom. We're talking on the order of femtometers, which is 10 to the power of minus 15 meters. That's 0.0000000000000000001 meters.
Wow, my brain hurts just trying to picture that. And you said it's incredibly dense too, right?
Oh, absolutely. Imagine squashing the entire mass of the Earth into a sphere just a few kilometers across. That's about the density we're talking about inside a nucleus.
The entire Earth squeezed into a tiny ball. That just blows my mind.
It's amazing, isn't it? In fact, the only things in the universe denser than atomic nuclei are neutron stars, which are collapsed remnants of massive stars.
Neutron stars. Let's save those for another deep dive, I think. Okay, so we know now that the nucleus is composed of protons and neutrons packed incredibly tightly together. But protons have a positive charge. And it's like charges repel each other, right?
Yeah.
So what's stopping the nucleus from just flying apart?
That's a great question. And it brings us to one of the most fundamental forces in the universe. The strong nuclear force, sometimes just called the strong force.
The strong force. I've heard of that, but I'm a little fuzzy on the details.
Well, the strong force is what binds those protons and neutrons together in the nucleus, overcoming their electromagnetic repulsion. It's incredibly strong, but it only acts over very, very short distances, like the size of the nucleus itself.
So it's like a super powerful glue that only works at extremely close range.
Exactly. Think of it like Velcro. When those nucleons are right next to each other, the strong force grabs them and holds them tight.
Okay, that makes sense. And this strong force, is it just between protons, or does it act between neutrons as well?
It acts between all nucleons, protons and protons, neutrons and neutrons, and protons and neutrons. It doesn't discriminate.
Interesting. So it's not just about overcoming the repulsion between the protons, it's also what holds the neutrons in place. So how do scientists actually measure how tightly these nucleons are bound together in a nucleus?
They use a concept called binding energy, which is essentially the energy required to completely separate all the nucleons in a nucleus.
So the higher the binding energy, the more stable the nucleus.
Exactly. A high binding energy means it takes a lot of energy to break that nucleus apart, making it more stable. We can even calculate this binding energy using Einstein's famous equation, EMCS.
EMCS, that's like the most famous equation ever.
It is pretty iconic, and it basically tells us that mass and energy are equivalent. They can be converted into one another.
So how does that relate to binding energy?
Well, when nucleons come together to form a nucleus, their total mass actually decreases slightly. This difference in mass is called the mass defect.
So some of the mass disappears when the nucleus forms. Where does it go?
It's converted into energy, and that energy is the binding energy that holds the nucleus together. So the mass defect, multiplied by the speed of light squared, gives us the binding energy.
So a tiny bit of mass goes missing, and in its place, we get the energy that keeps the nucleus from flying apart.
Wow. It's pretty mind-blowing when you think about it. And this binding energy per nucleon, it's not the same for all nuclei.
Right, you mentioned something about a sweet spot earlier.
Exactly. It turns out that nuclei with intermediate mass numbers, around 56 nucleons, have the highest binding energy per nucleon.
So those nuclei are the most stable.
Precisely. Iron 56, for example, is one of the most stable nuclei in the universe.
Okay, that makes sense. So if lighter nuclei can fuse together to get closer to the sweet spot, they release energy.
Right. And if heavier nuclei can split apart to get closer to that sweet spot, they also release energy.
That sounds a lot like those processes you mentioned earlier, fusion and fission. We'll get to those later, I guess. So we've talked about binding energy, but what about the actual structure of the nucleus? How are those protons and neutrons arranged?
Good question. And just like electrons in an atom occupy different energy levels or shells, nucleons in a nucleus also occupy specific energy levels.
So it's kind of like a miniature solar system inside the nucleus, with the protons and neutrons orbiting in specific shells.
That's a simplified way to visualize it, but it's not quite accurate. The nucleons are not actually orbiting in the traditional sense. It's more like they exist in a sort of cloud, and their energy levels are quantized, meaning they can only have specific discrete values.
Quantum mechanics strikes again. Okay, so there are these shells, and each shell can only hold a certain number of nucleons.
Exactly. And just like filled electron shells lead to particularly stable atoms like the noble gases, filled nuclear shells lead to very stable nuclei. These numbers of nucleons that correspond to filled shells are called magic numbers.
Magic numbers. Okay, what are these special numbers?
The magic numbers are 2, 8, 20, 28, 50, 82, and 126. If a nucleus has a magic number of protons or neutrons, it's exceptionally stable.
Like extra stable.
Yes, much more stable than nuclei with other numbers of protons or neutrons.
So it's like there's something special about those particular numbers of nucleons.
Exactly. It's all due to the complex interplay of the strong force and quantum mechanics within the nucleus.
Okay, I'm starting to see how this all fits together. But we know not all nuclei are stable, right? What happens when they aren't?
That's where radioactivity comes into play. When a nucleus is unstable, it tries to become more stable by emitting particles or energy. We call this process radioactive decay.
Radioactive decay. So the unstable nucleus basically spits out something to try to reach a more stable configuration.
That's a good way to put it. And there are several different types of radioactive decay, each with its own unique characteristics.
Okay, tell me about them. What are the main types?
One of the most common types is alpha decay. In alpha decay, an unstable nucleus emits an alpha particle, which is essentially a helium-4 nucleus.
A helium nucleus. So it's like a tiny helium atom flying out of the bigger nucleus.
Yes, that's a good way to visualize it. The alpha particle has 2 protons and 2 neutrons, so it's relatively heavy and carries a positive charge.
And when it flies away, what happens to the original nucleus?
Well, because it loses 2 protons and 2 neutrons, its atomic number decreases by 2, and its mass number decreases by 4.
So it actually transforms into a different element.
Exactly. That's what's so remarkable about radioactive decay. It can actually change one element into another.
Wow. So alpha decay is one way for an unstable nucleus to become more stable. What are some of the other ways?
Another common type is beta decay. And there are actually 2 types of beta decay: beta minus decay and beta plus decay.
Okay, what's the difference?
In beta-minus decay, a neutron in the nucleus transforms into a proton, emitting an electron and an antineutrino in the process.
So a neutron turns into a proton, and the nucleus essentially gains one positive charge. What about beta plus decay?
Beta plus decay is the opposite. A proton in the nucleus transforms into a neutron, emitting a positron and a neutrino.
A positron, what's that?
A positron is the antiparticle of an electron. It has the same mass as an electron, but a positive charge.
Antimatter. I knew this stuff would get weird eventually. Okay, so in beta plus decay, the nucleus loses a proton and gains a neutron. Is there another way for that to happen without involving antimatter?
Yes, there's a process called electron capture. In this case, a proton in the nucleus captures an electron from one of the atom's inner shells.
So it sucks in an electron from its own electron cloud.
Exactly. And that proton then combines with the electron to form a neutron, emitting a neutrino in the process.
Interesting. So beta plus decay involves emitting a positron, while electron capture involves absorbing an electron, but the net effect on the nucleus is the same.
Precisely. Both processes result in the atomic number decreasing by 1, while the mass number remains the same.
Okay, so we've got alpha decay and beta decay. What other ways are there for a nucleus to become more stable?
Another important process is gamma decay. In gamma decay, an excited nucleus releases energy in the form of a gamma ray.
A gamma ray. Those are like really high energy photons, right?
Exactly. Gamma rays are part of the electromagnetic spectrum, just like light and X-rays, but they have much higher energies.
So it's like the nucleus is releasing a burst of pure energy. But unlike alpha and beta decay, gamma decay doesn't change the composition of the nucleus, right?
That's right. It just releases energy, usually after a nucleus has undergone alpha or beta decay and is left in an excited state.
So it's kind of like a nuclear burp, letting out some excess energy.
That's a colorful way to put it. And sometimes a nucleus has to go through a whole series of these decays before it reaches a stable configuration.
Like a chain reaction, but for radioactive decay.
Exactly. We call these radioactive decay series. A classic example is the decay of uranium-238, which goes through a long chain of alpha and beta decays, eventually ending up as stable lead-206.
So uranium eventually turns into lead after millions of years of radioactive decay. That's pretty wild. Okay, so we know that unstable nuclei decay, but how do scientists measure how quickly this decay happens?
We use a concept called half-life. The half-life of a radioactive isotope is the time it takes for half of a sample of that isotope to decay.
So if we start with 100 grams of radioactive substance with a half-life of 10 years, after 10 years we'll have 50 grams left.
Exactly. And after another 10 years, we'll have 25 grams left, and so on. It's an exponential decay process.
So isotopes with short half-lives decay very quickly, while those with long half-lives decay much more slowly.
That's right. And knowing the half-lives of different isotopes is incredibly useful for all sorts of applications, from medical imaging to dating ancient artifacts.
Dating ancient artifacts, how does that work?
It's based on the fact that radioactive isotopes decay at a known rate. By measuring the amount of a particular radioactive isotope in a sample and comparing it to the amount of its decay product, we can calculate how long it's been since that sample was formed.
So we can use radioactivity to figure out how old things are, like fossils and ancient rocks. That's amazing. Okay, so we've talked a lot about the nucleus and radioactive decay. Now, what happens when this radiation from these decays interacts with living things?
That's a crucial question because radiation can have both beneficial and harmful effects on biological systems.
Right, we hear a lot about the dangers of radiation.
And for good reason. High doses of radiation can be very dangerous. But it's important to understand that we're exposed to low levels of radiation all the time, from natural sources like cosmic rays and radioactive elements in the Earth's crust.
So there's a natural background level of radiation that we're constantly exposed to.
Exactly. And our bodies have evolved to deal with this low-level radiation. But it's the high doses of radiation that we need to be careful of.
Okay, so what are the specific ways that high doses of radiation can harm living tissue?
Well, radiation can damage cells by ionizing atoms and molecules within them, which can disrupt cellular processes and even lead to mutations in DNA.
So it's like tiny bullets flying through our bodies and knocking things out of whack at the molecular level.
It's a good analogy. And the severity of the damage depends on the type of radiation, the dose, and the part of the body that's exposed.
So different types of radiation have different levels of danger.
Exactly. Alpha particles, for example, are very heavy and carry a double positive charge, so they can do a lot of damage if they're ingested or inhaled. but they're easily stopped by a sheet of paper or even your skin.
So alpha particles are dangerous if they get inside your body, but not so much from an external source.
That's right. Beta particles, on the other hand, are lighter and can penetrate further, but they do less damage per interaction. And gamma rays are the most penetrating, able to travel through thick layers of material, but they also interact less frequently with matter.
So it's a trade-off. The more penetrating the radiation, the less likely it is to interact with your body, but if it does interact, it can cause more damage.
That's a good summary. And of course, the dose of radiation is also critical. The higher the dose, the greater the potential for harm.
Okay, so how do scientists measure the dose of radiation someone has received?
We use units like the Gray and the sievert. The Gray measures the absorbed dose, which is the amount of energy deposited by radiation per unit mass of tissue. The sievert takes into account the biological effectiveness of the radiation, meaning how much damage it can do.
So sieverts are a better measure of the potential harm from radiation exposure.
Yes, exactly. And it's important to remember that radiation can also be used for beneficial purposes.
All right, we use it in medicine all the time for imaging and treatment.
Exactly. X-rays, CT scans, and PE scans all use radiation to create images of the inside of the body. And radiation therapy uses high doses of radiation to kill cancer cells.
So it's a double-edged sword. Radiation can be both harmful and incredibly useful, depending on how it's used and controlled. Okay, so we've covered the nucleus, radioactive decay, and the effects of radiation on living things. Now let's move on to another fascinating aspect of nuclear physics. Nuclear reactions.
Right. Nuclear reactions are essentially processes where the composition of a nucleus is changed by bombarding it with another particle.
So instead of just spontaneously decaying, like in radioactivity, we're actively forcing a change in the nucleus.
Exactly. And there are many different types of nuclear reactions depending on the particles involved and the energy of the interaction.
Okay, give me some examples. What are some common types of nuclear reactions?
Well, one common type is neutron capture. In this case, a nucleus absorbs a neutron, which can lead to the formation of a heavier isotope of the same element.
So you're essentially adding a neutron to the nucleus, making it a bit heavier.
That's right. And sometimes this neutron capture can make the nucleus unstable, causing it to undergo radioactive decay.
It's like a chain reaction, but instead of a chain of decays, it's a chain of neutron captures and decays.
Exactly. And this process is crucial in nuclear reactors and the production of certain radioactive isotopes used in medicine and industry.
So by bombarding nuclei with neutrons, we can create new elements and isotopes that don't exist naturally. What about reactions involving other charged particles?
Well, if you want to bombard a nucleus with a charged particle, like a proton or an alpha particle, you need to overcome the Coulomb barrier.
The Coulomb barrier, what's that?
It's the electrostatic repulsion between the positively charged particle and the positively charged nucleus. Think of it as a force field around the nucleus that you have to break through.
So you need to give the particle enough energy to overcome this repulsion and get close enough to the nucleus for the strong force to take over.
That's exactly right. And this is why particle accelerators are so important in nuclear physics research. They allow us to accelerate particles to incredibly high speeds, giving them enough energy to overcome the Coulomb barrier and interact with nuclei.
So particle accelerators are like giant slingshots, flinging these tiny particles at incredible speeds to smash them into nuclei.
It's a pretty good analogy. And these high-energy collisions can create all sorts of exotic and fascinating phenomena, helping us understand the fundamental building blocks of matter.
Okay, I think I'm starting to get a grasp on the basics of nuclear reactions. Now let's talk about two of the most well-known and powerful nuclear reactions, fission and fusion. Starting with fission. What exactly is it?
Nuclear fission is the process of splitting a heavy nucleus into two or more lighter nuclei, releasing a tremendous amount of energy in the process.
So it's like smashing an atom, but with a lot more energy released.
It's a bit more controlled than just smashing an atom, but yes, it involves splitting a nucleus and releasing a huge amount of energy. A classic example is the fission of uranium-235.
Uranium-235.
Yeah.
That's the stuff used in nuclear bombs and power plants, right?
That's right. Uranium-235 is a radioactive isotope that, when it absorbs a neutron, can split into two smaller nuclei, releasing several neutrons and a lot of energy.
Okay, so one neutron goes in and several come out. What happens to those extra neutrons?
Those neutrons can go on to cause further fission events in other uranium-235 nuclei, creating a chain reaction.
The chain reaction. So it's like a domino effect, with one fission triggering more and more fissions, releasing more and more energy.
Exactly. And that's the principle behind both nuclear bombs and nuclear power plants.
Okay, so how do nuclear power plants control this chain reaction so it doesn't become a bomb?
They use control rods to absorb some of the neutrons and slow down the chain reaction. They also use moderators to slow down the fast neutrons released during fission, making them more likely to be captured by other uranium-235 nuclei and cause further fissions.
So control rods are like brakes, and moderators are like speed bumps for neutrons.
That's a good way to think about it. And by carefully controlling the chain reaction, nuclear power plants can harness the energy released from fission to generate electricity.
Okay, so fission is splitting a heavy nucleus to release energy. What about fusion? That's the opposite, right?
Exactly. Nuclear fusion is the process of combining two light nuclei to form a heavier nucleus, also releasing a lot of energy.
And this is what happens in stars, right?
That's right. The sun and all other stars are powered by nuclear fusion. In the sun, hydrogen nuclei are constantly fusing together to form helium, releasing a tremendous amount of energy in the process.
So the sun is basically a giant fusion reactor in the sky.
That's a good way to put it. And it's been shining for billions of years thanks to the power of fusion.
Incredible. But why is fusion so much harder to achieve here on Earth than fission?
The main challenge is that you need incredibly high temperatures and pressures to get nuclei to fuse together. Think of it like trying to smash two magnets together, but the magnets are repelling each other. You need a lot of force to overcome that repulsion.
So it's like trying to force two positively charged nuclei to get close enough for the strong force to take over and bind them together.
Precisely. And the temperatures required for fusion are on the order of millions of degrees. That's hotter than the core of the sun.
Millions of degrees. How on Earth can we create and contain such extreme temperatures?
Scientists are working on different approaches to achieving controlled fusion. One approach is magnetic confinement, where powerful magnetic fields are used to contain the superheated plasma in which fusion occurs.
Plasma. What's that?
Plasma is a state of matter where atoms are stripped of their electrons, so you have a mix of positively charged ions and free electrons.
So it's like a superheated soup of charged particles.
That's a good way to visualize it. And magnetic confinement is one way to keep this superheated plasma from touching the walls of the reactor and cooling down.
Okay, what other approaches are there?
Another promising approach is inertial confinement, where powerful lasers or particle beams are used to compress and heat tiny pellets of fusion fuel, causing them to implode and fuse.
So it's like creating a mini star in the lab for a brief moment.
That's a good analogy. And both magnetic and inertial confinement fusion are active areas of research, with the ultimate goal of achieving sustainable fusion power here on Earth.
So while fusion power is still a long way off, it holds immense potential as a clean, safe, and virtually limitless source of energy. It's amazing to think that the same process that powers the stars could one day power our homes and cities.
Absolutely, and that's the beauty of nuclear physics. It's a field that deals with the most fundamental building blocks of matter, the forces that govern their behavior, and the incredible processes that occur within the nucleus.
It's been a truly mind-blowing journey into the heart of the atom.
It really is, and we've only just scratched the surface of this vast and fascinating field.
But hopefully this deep dive has given you a better understanding of the key concepts of nuclear physics, from the structure of the nucleus to the power of fission and fusion.
And maybe even sparked a little bit of wonder and curiosity about the universe and the amazing forces at play within it.
And with that, we'll wrap up this episode of The Deep Dive. Thanks for listening, and we'll see you next time for another deep dive into the mysteries of the universe.
Until then.